Welcome to the video lecture of Meeting 2, Problem 3, the Monty Hall problem. You are told that a prize is equally likely to be found behind any one of three closed doors in front of you. Then, you point to one of the doors. Your friend opens for you one of the remaining two doors, after making sure that the prize is not behind it. At this point, you can either stick to your initial choice, or switch to the other unopened door. You will win the prize if it lies behind the door of your final choice. Using laws of conditional probability, the best strategy for this game is to always switch from your first choice. Here's why. Using a probability tree diagram, let us identify the three events. The first event, which we will denote as event P, is the placement of the prize. The placement of the prize can be in any of the three doors. Let us use a subscript, I, to indicate which door the prize is placed. Take note that these outcomes are equiprobable, meaning, the chances of being placed in door 1 is the same as with door 2 and door 3. Thus, we can compute the probability P of P sub I, where I can be 1, 2 or 3, which is just equal to 1/3. Next, we proceed with the event of you choosing one of the three doors. We will denote this event as event C. Now let us assign the probability expression. Since for every P sub I there are three C events, we can write the probability expression as P of C sub I given P sub I. Also note that your choice of a door is independent of the placement of the prize. We formally say this as event C is independent of event P, and the probability P of C sub I given P sub I is just P of C sub I. Again, each of the doors have equal chances of getting picked. Thus, we can easily compute P of C sub I, where I can be 1, 2 or 3 as 1/3. Now, after choosing a door, we will proceed to the event of your friend opening a door, which we will denote as event O. The expression for the probability is P of O sub I given C sub I intersection P sub I. Here, it is important to note that your friend only opens a non-winning door and he cannot open your chosen door. This leads us to two possible scenarios. First scenario is when you have chosen the winning door from which he can still choose among the two remaining doors. The other scenario is that you have chosen the wrong door and he is then forced to open the remaining door, which does not contain the prize. In the first scenario, there are two possible outcomes. Thus, assuming the two remaining doors have equal chances of being opened, the probability is just 1/2. On the other hand, for the second scenario, your friend is always forced to open the remaining non-winning door. Since that remaining non-winning door is always the choice in scenario 2, the probability is 1. We can further expand our tree by including the outcomes when we stay or switch. Then we can identify the winning and the losing paths. If we always decide to stay, we have 6 possible winning paths. The probability for each path can be computed as a product of the branches. Then the total probability is just the sum of the probability of the winning paths. We get 1/3. If we always decide to switch, we again have 6 possible winning paths. The probability for each path can be computed as a product of the branches. Then the total probability is also just the sum of the probability of the winning paths. We get 2/3. Using the probability tree diagram, we can compute other possible strategies for the Monty Hall problem. For example, suppose we decide to always pick door 1, then stay if door 2 is opened, or switch if door 3 is opened. We have 2 winning paths. The probability of each path is just the product of the probabilities along its branches. The total probability would be the sum of probabilities of the 2 winning paths. However, in this example, it is important to note that the probability of choosing a door is no longer equiprobable among the three doors, since we always initially choose door 1. That changes the total probability to 1/2. This strategy is better than always staying, but not as good as always switching. This problem has puzzled a lot of people due to the misconception that after one door is opened, the odds or the risk is just increased from 1/3 to 1/2. This would be true if only all the paths are equiprobable. However, we already know that the mechanics of the game changes the probability of opening the doors. In solving these types of problems, it is important to ask yourself questions like: which of these events are independent? Does this event always occur? Are these outcomes equiprobable? Thank you for watching.